Hello and welcome to Video Notes 6.4, where we're going to talk about influential points and lurking variables. So last lesson we discussed subsets and extrapolation. And so here we're going to look at two of the most common sort of pitfalls in our linear regression work here. So we're going to start off with just some definitions to have a firm understanding of what these words mean. So what is an influential point? That would be a point that results in a very different slope for a regression model if it is removed. Okay, so if you're looking at it and you're like, if I pull that point out of the scatter plot and just remove it, suddenly my regression model has a vastly different slope, then that would be considered an influential point. There's obviously degrees to this, so some influential points might be very influential and some might be sort of influential, so we'll get a little bit into that. Outlier, we've talked about that before, and we've been just sort of coming up with it appears to be an outlier. The actual sort of strict definition in a scatter plot is an outlier is a Y value that's very far from its predicted value, which results in a large initial residual. So a large residual is the indication of an outlier. And again, there's degrees to that. How large is large? Well, you can have a vast outlier. You can also have one that's sort of an outlier. There isn't really a benchmark necessarily for this. The last new definition for us here is leverage. Leverage, data values whose X values are very far from the mean or average of our X values are considered to have high leverage, okay? These are sort of like outliers, but in the X direction rather than in the Y direction. So we don't really have an idea of like a residual in terms of X's necessarily, but if there were that idea, then that would be the sort of the case for a high leverage point. So let's go ahead and sort of go through and see some examples of these different flavors of points and sort of see some overlap between them, because maybe as you're reading these, you might be kind of going like, is it possible that an outlier is also influential or is a high leverage point also like there's ways to sort of talk about those things. So let's get into it. So when a point has a Y value that's very far from the rest of the data and thus its predicted value of Y hat, you have an outlier, okay? Outliers which have a large initial residual will often, but not always, have a strong effect on the regression line as influential points, all right? So in this case, as it's sort of saying, there's outliers tend to be influential points. It's not always the case, but it's oftentimes the case. So what we see here in our scatter plot, this is an example of comparing votes in different counties in Florida from the 2000 presidential election. If you don't know about the 2000 presidential election, maybe read up on it because it was a bit controversial and Florida played a huge part. So what this is doing for us is comparing actually the number of votes in each county that Ralph Nader got, he was a third-party candidate, compared to Pat Buchanan, also a third-party candidate. And so you can see that what I have there is two different regression models that are there. I'll explain the two different regression models in just a moment here. But what you also probably noticed is that we have a huge outlier up here, there. That is Palm Beach County, okay? As you can see, there's a larger number of Buchanan votes compared to Nader than expected from our model. So which model is sort of taking that outlier into account? That would be, I'm going to go ahead and go over it in red. This line right here is the one that is using that outlier value there and taking it into account. So you can notice that in order to sort of compensate for this ginormous Y value change here, we've had to sort of make that model go up. So right here, we have a large residual. And if you recall, the definition of sort of what a least squares residual model is doing is that it is taking these residual values, squaring them, and trying to minimize the total sum of all of those values. So the line has to be sort of clicked up a bit to try to, at best, make sense of that large residual, trying to make it as small as possible while not getting too far away from all the other data points there. Now, it turns out if you just say, I don't want that point there, I want to just say, no, thank you. What if I just go by? I don't want to even look at that. What it does is it moves the residual model down like so, and going over this in green. So it now will just sort of hinge down that line a bit there and change that slope by a significant amount there. How much exactly? Well, I have the values here for you if you were so inclined to look. So with Palm Beach County in there, we have a slope of 0.14, okay? Without it, it drops it down to 0.1. Now, in terms of just raw magnitude, look at it like, so it just dropped by 0.4. That's not a very big number. But when you think about the slopes we're dealing with, okay, we're only dealing with slopes that are less than 1 here, much less than 1. As it turns out, the change in that slope is over 28% change. So that's a huge amount. To change it by over a quarter of the amounts there, that's a large enough amount that we would sit there and say, ooh, that is a big change. So remember to think about scale here. In this particular case, since we're dealing with slopes that are much smaller, smaller than 1 here, then these kinds of changes are going to be big. The other thing you might have noticed that we were looking at here is the R squared also vastly change, and that should make sense to you because R squared is sort of talking about how much our model is explaining the variability in our values here. So before that huge residual there, our model does not do a very good job of explaining that, okay? But if you take that away, you can see that most of our data points are falling very close to that green regression line, in which case we are doing a really good job at explaining that. So there you have it. So outliers in this sort of scenario can be influential points. You can also see how like much smaller outliers maybe don't adjust your regression model. If in fact the data point was actually down here instead, that's like, okay, that is kind of, sorry, that's maybe not very far. Let's go like here. You might look at it and go like, oh, that is a bit different, a bit further out than I was expecting. But if you were to have removed that, then it probably wouldn't affect the line slope as much. So that's something to think about as like outliers. There's degrees of outliers, right? And because of that, it kind of affects how influential they would be. All right, why don't we go ahead and keep moving along here? So that is outliers and how they can become influential points. We're going to look at here now the other type of point that we were discussing that could be an influential point, which is a high leverage point. So a related pitfall revolving around points with high leverage, where the x value is very far from the average x value. So these may not always be influential points, but they might. I got some examples here. So first, let's look at this scatter plot over here on the left. We're going to take a look at that one first. And so what we have here is this single point out here that is a high leverage point. How do I know that? Well, let's go ahead and take a look. The average of our x values, if we were to sort of put that all in, would probably be like here. X bar would be like right about there-ish, we'll say. I'm just going to eyeball it. Okay, so the difference in between these things here, that right there, that is representing the high leverage because the distance that point is from the average of all the x's is pretty far. And so the further away it is, more leverage it has. So this is a point we would determine to be high leverage. Now, is it an influential point? Well, that's where you'd have to start thinking about what does my regression model look like? I don't actually have the data here, but I can eyeball pretty quickly that it appears that the least regression line might be something sort of like that there. And we can see that that particular point falls on or very close to the regression line. So if I were to remove that high leverage point, my line is not going to move very much at all. The slope is basically going to stay the same because that point kind of falls along the trend of the rest of the data. Now, what's interesting here is that that particular point there is actually doing a bang-up job at increasing our R-squared value. And the reason for that is because our model is doing a better job at predicting things and explaining things for bigger differences in our x's. If that point wasn't there and I was just looking at this smaller cluster, it's like, okay, yeah, I've got some changes in my x's and I can see some changes in my y's. But this particular one, that's a huge change in our x's that we might see, and it's nailing that change in the y that you would expect. So because of that, it's bumping up that R-squared value quite a bit. Which means that if we were to remove it, removing that point, that's going to weaken our R-squared value in this particular case. But it doesn't really change the actual model itself by removing it. That's why it's not influential. So in this particular case, we would deem this not influential. All right, but let's look at some examples where it is influential. So here we have a scatter plot of comparing adult shoe sizes to their IQ. You would assume that there probably is not much of a correlation between those two things. Somebody with bigger feet, if they are an adult, doesn't necessarily mean they have a higher IQ or vice versa. Obviously, if we were to grab a sample that included children and adults, then we might see a correlation there. But in this particular case, we're looking at only adults, okay, whose feet are not growing any longer. And so if in fact these particular variables did not have much of a correlation, then if we were to run a regression line, we would end up getting just a horizontal line that goes through sort of the middle of our data because there's really no correlation. So there wouldn't be a slope. We wouldn't expect there to be on average sort of a decrease or increase predicted if you were to increase some shoe size, you know? So what you see there are the black lines. Those are the models that would be appropriate if this particular X was tossed in. So now we're going to play a little sort of what if game. So it's like, all right, all these little dots over here, that's the original sample. What if we pulled somebody who had ginormous feet and was a genius, okay? If Shaquille O'Neal was a genius, maybe he is, I don't really know what his IQ is, and we threw him in here, how does that affect things? Well, as we can see here, that is going to affect our model by making it change from a slope very close to zero to a slope that is now very much positive, okay? And it's because that particular point is high leverage. How do I know it's high leverage? The same way I knew it was high leverage from before. If the mean of our X values is about here, we can see that the distance between them is very large. It is high leverage. It's the same thing if instead maybe we got somebody who had very large feet and was a bit of a dope. And we could see that's there here. Again, if we're looking at that our X bar is about 7.5, then this is high leverage. And we can see how, depending upon where you place this very high leverage point, that it's going to change what our model is. So above sort of the rest of our data, it makes a regression line that becomes a positive slope. If we place it, because they're kind of a dum-dum, down below, then we end up with a regression line with a very much negative slope in this case. So both of these scenarios here, they are high leverage points that are also very much influential. Oh, I can't spell influential. Very much influential because it changed the slope of our regression model just by adding this point in, or the vice versa. If we took it away, then in fact, all of these slopes here, so instead of having a positive slope here, it would go back to being very flat. If we remove this point, instead of having the negative slope, it goes back to being very flat. And once again, these particular points are also messing with our R squared, okay? So in these second two scatter plots, they do act influential because they greatly decrease our R squared and alter the slope. So that's what's going on there. So you might be wondering, hey, well then how do I know? You just sort of said like there's a lot of degrees to sort of influential versus high leverage versus outliers. Like how do you know when you have something that is high leverage or an outlier that is also influential? So the general rule of thumb is that it is that a point must have at least some leverage and be an outlier in order to be an influential point. We'll sort of talk a bit more about that because some is still a very subjective idea, some leverage, and like an outlier, we've talked about being kind of subjective as well. So we actually will have an activity in class where we're going to tinker around and sort of play with this idea of like a seesaw activity in this particular case. All right, let's go ahead and move on to the backside. All right, here we are on the backside where we're going to talk about lurking variables, okay, which you might have talked about in other classes. And so this is sort of a review of that. So lurking variables are a hidden variable that simultaneously affects both variables in an association, accounting for the correlation that may appear between the two, okay? So let's consider this first scatter plot that's given here. We're gonna go ahead and compare the square root of doctors per person and life expectancy, which is really kind of comparing how many doctors per person, life expectancy, but obviously we've re-expressed this to try to make it look a little more linear. So we can see there's a positive association between these things, okay? So what this means is that as the number of doctors per person increases, so does life expectancy. Kind of makes sense. That doesn't seem too surprising, right? More doctors means more health, people live longer, right? But does this mean that if a country has more doctors, that we should expect the life expectancy if a country has more doctors, that it causes the life expectancy of a population to increase? Do you think that, like, for instance, if there's a country that's like, ooh, your life expectancy is only 55 years old, ship doctors over because that will help. That'll cause the life expectancy to skyrocket. What do you think? Hopefully you said no. Remember that when we're talking about looking at scatter plots, we can never sit there and say that that thing caused that thing unless we know it came from a well-designed experiment with those four principles of comparison, control, replication, and randomization. If it doesn't have those elements, then we can't do that. So if we're just observing data like this, we have no way of actually saying causation is happening, just correlation. Now, this one is a little bit tricky, but then it kind of gets kind of funnier when you sort of think about other scenarios. So here's another way to frame this question. So let's check out this scatter plot. This time around, we're looking at an association between the square root of TVs per person, okay, and life expectancy. By eyeballing it, it looks like the association is much stronger, actually, than the above about doctors per person. So in this case, we're looking at, hey, if you add more TVs to a country, your expectancy, life expectancy, goes up. And again, would it be appropriate to sit there and say, I think actually we should just ship over that country you said that only people live to like 50 years old. What if we just ship over, like Samsung just ships them a bunch of TVs that would help the life expectancy. People live longer, right? That's ludicrous to think about. There's no way that TVs are causing people to live longer. So what's going on here? Well, what's likely happening here is that we're dealing with a lurking variable. I want you to pause the video and think for a moment. Can you brainstorm a lurking variable that links together this idea of having more TVs means people live longer? So hopefully you said or brainstormed something like this. There might be even other scenarios that we can sort of discuss to see if it makes sense. But the one I came up with is the wealth of the country seems to be the lurking variable. So as wealth increases in a country, then people can afford to buy more televisions, which increases the number of televisions per person. And on the other hand, more money means they could probably take better care of themselves, eat healthier, go to the doctor more often, afford the medicine and drugs, the things that will keep them alive. So that's sort of the idea. And that's also sort of why like the number of doctors kind of comes in, is like more doctors come from countries that have more wealth. There's less doctors in countries where they're more impoverished, actually, is what's going on there. So it's really, really critical that we remember through all this that correlation does not prove causation. Causation, remember, can only be proven through experiments. Not proven, but like inferred through experiments, well-designed experiments. So we don't want to fall into that trap that where we see these two variables related to each other and go in and go like, oh, that's causing that to happen. So that's really important, okay? But since things are related to each other, it actually is great that you could use them to still make predictions. You know, the predicting power for these things is still pretty good. So like it doesn't mean you can't make predictions based off of these things. It's not that you can't tell me, oh, a country has this life expectancy and I could probably predict for you with relative, accuracy how many TVs per person they have. But it just means I don't believe that these two things are causing each other to have this relationship. So to finish it off, I want you to try out sort of thinking about these things here. So we have here 4 scenarios, and we're going to try to brainstorm lurking variable or variables, if you come up with them, that help you out with this. So for this first one, there's a positive association in the amount of damage at a fire scene versus the number of fire trucks that show up to the scene. So in other words, the association between these things is positive. As there's more trucks showing up, there's more damage, or vice versa. What would maybe be the cause of that? Because at first, you might look at that and go, well, my house catches on fire. I don't want trucks to show up because they're just going to cause damage. That's completely ludicrous. So what maybe is actually going on here? Next one, age at which baby first learns to crawl versus the average outdoor temperature for the city they live in. Positive association, so that would be in this particular case, negative this way, right? Positive association, monthly number of drownings that occur versus ice cream consumption. So as ice cream consumption goes up, so do the drownings. And then the last one, foot size versus reading performance. That's a positive association. So in school children, bigger feet are causing people to read better? Question mark? So I want you to brainstorm a lurking variable in each of these scenarios, because you're going to come into class and you're going to talk with your neighbors about what did you brainstorm and see if they match with each other, or maybe you came up with something that's more unique and interesting and has to be shared with the rest of the class. With that said, we will see you in class.